Yeah, I'm fine, everyone. Let's start off. Great. So last thing that we did was a fuse. Right. We have done different things like maximum power transfer theorem, bulbs, combination of batteries. Today we'll be doing electrical instruments. There's a bit of a theory there, but quite an important topic because this thing comes in current electricity, also can come as a electrical instrument. There's a separate subtopic. So let's say this. It's not tough. It is easy. But the main thing, you really need to understand how and why the equipment is working. As long as you understand, questions will be straightforward. Great. So let's go ahead. Now, in electrical instruments, right, technically, there is only one instrument that we actually have. From that, we have to create everything else. So that is a galvanometer. We have a construction of galvanometer in magnetism. We will see that later on. So what does a galvanometer does? It's a current sensitive device. Where the current flowing to the galvanometer is proportional to the angle deflected by the needle. So we will see the construction later on. So basically, there will be some kind of a magnet, and there is a coil, and there is a small needle kind of thing connected to the coil. Angle deflected by the needle. So whenever the current passes, the magnetic repulsion will rotate the coil, and then you get this thing. So that we will not deal with it right now. So one thing is clear. Somehow the angle current is proportional to the angle theta. So what happens is, if you see a galvanometer, we have readings like, let's say, 0 milliampere, 1 milliampere, 2 milliampere, 3 milliampere, again 2 milliampere, again 1 milliampere. So if the current flows from left to right, then the needle will deflect towards right. Yeah, but we have other types of galvanometers also where they will always deflect in the same direction. Same thing. Suppose the current flows from right to left, then the needle would deflect this way. So this thing gives you two things. One, it will tell you the direction of the current. Second, it will also tell you how much magnitude. So if the needle goes to the right, we know the current is going to the right. If the needle goes to the left, we know the current is going to the left. So somehow this galvanometer measures the current in the direction. That we will not worry about right now. The symbol for the galvanometer is this, a G with a circle around it. This is IG and this is RG. So RG is the resistance in galvanometer. Because it is made of some wire, coils and all, that has its own resistance. IG is the current in the galvanometer. G is the subscript. Now, great, we have a device which can measure current, but the problem is, whenever you want to make this galvanometer, right, you have to use pretty thin wires to make it very sensitive. And when you use very thin wires, they have large resistance, right? And if you send current through them, what will happen? You'll get a lot of heat and the thin wires will melt. So these things have a problem. They cannot measure large currents. So the range is around microampere to milliamperes. So galvanometer measures very small currents. If you look at your house ka AC, right? AC takes almost 16 amperes ka current. So galvanometers, these things are pretty bad, right? They cannot withstand large currents. And sometimes they'll use the word full scale deflection. Full scale deflection meaning the maximum IG in the current. So maximum current is flowing in the circuit, meaning anything more than this, the circuit will burn down. This part is clear. So we have something called a galvanometer, which cannot measure large currents. It can measure current, but it can measure only up to milliamperes. So somehow we have to make this galvanometer measure larger currents, because in real life, currents will be in the ampere range. So if you see in the entire instrument, this is the only thing that you have. Everything else is constructed from this guy only. And this construction we'll see in magnetism. Clear with this? Next page, going ahead. So the first device we have is an ammeter. So ammeter, it measures current. And is constructed by shunting. So shunting meaning keeping in parallel. So that is a technical word for it. Right? It measures current and is constructed by shunting a small resistance to the galvanometer. So you can read it like this. It is constructed by keeping a small resistance in parallel to the galvanometer. So they'll just use the word shunt resistor, means you kept it in parallel. That's the meaning of it. Few things. One, ammeter must be placed in series. So whichever device you're trying to measure the current, place it in series so that they have same current. Second thing, an ideal ammeter has zero resistance. So how do this thing works exactly? So we have a galvanometer. You take a very small resistor. So this is RG, this is R shunt. So this whole package, right, is what we call as ammeter. You're trying to measure this capital I. So this whole package is what we represent with the capital A symbol. That's your ammeter. So an ammeter is nothing but a galvanometer with a resistance in parallel. So this is called a shunt resistance. Shunting meaning parallel. Just keep that in mind. So what is the story now? When this current comes here, this will be IG. The remaining current will flow through this, I minus IG. Now we can clearly see RG and R shunt both are in parallel. So IG into RG must be equal to I minus IG into R shunt. Rearrange the terms, we will end up with IG plus 1 by RG by R shunt. There, we got a formula between them. Now, what does this mean exactly? Like, and how do we measure current from here? We'll come back to this page. Listen to this thing. What we do something called a calibration. So basically, we are manipulating. What happens in devices, right? They always measure something, but they show something else. Let me give an example. When you stand on a weighing machine, what does it actually measure? If you go and stand on a weighing machine, it measures what? It measures normal reaction. It doesn't measure gravity. It doesn't measure weight. It doesn't know what is your weight, isn't it? If you go and take your school bag and stand on it, how does it know what is your weight and what is your school bag ka weight? It measures normal reaction. And what it does, so when you go and stand on it, so the machine is calibrated or the machine is manipulated to show something else. And it shows whatever value that it measures, it divides by G, and you think that is weight, isn't it? So a weighing machine doesn't measure weight, it measures normal reaction and it shows N by G. I hope you're getting the difference. So when we were in IIT first year, we had a project called anemometer. It was we have to make a small, a prototype which will measure the wind speed anemometer device. So I and another two friends, we came up with a very standard design. We kept some 3 cups kind of thing here. So when the wind blows, the cups will rotate. And then what we did, we connected this to a dynamo. So when the cups rotate, the dynamo, rotates, and then we get a voltage across the dynamo. So the idea was we want to measure the wind speed versus the voltage. So in IIT Madras, we have an aeronautical department. In that, they have a wind tunnel, so which can generate wind speeds from 5 to 120 kilometers per hour. So we took this setup, meaning there are other people also did this. So we all went there. We requested the HOD, and he gave us, like half a day time to do the calibration. So we are sitting there in that whole wind tunnel thing, and they started the different wind speeds. They started with 5 kilometers per hour. Then we started measuring the voltage. So we got something like 0.2 or something. Then when the wind speed is 10, we got one more value. 15, one more value. 15, 20, 30, we did till 60. You're getting what we did? Then we plotted all these values on a particular graph, and it was coming something of this sort. So we found a relation between the wind speed and the voltage. And it's not perfect, actually. It got messed up. We have manipulated the data, but we got something of that sort. So the idea is this. Now, if I know what is the voltage, from there I can figure out where is the wind speed, isn't it? For example, let's say the wind speed comes out to be a proportional to W square is proportional to voltage, something of this sort example. So if I know what is the voltage, can't I find the wind speed? So we have manipulated. So from the voltage, you're trying to find the wind speed in reverse now. Right? It is not a great design, but we write something. So something similar we are doing here. So what we are doing here, right? We are manipulating this galvanometer to show you the capital I. So the capital I is Ig plus 1 plus Rg by R shunt. This factor is your multiplying factor. Which you can actually adjust. You can change the value of Rg, R shunt by adding resistances and all. Let me show an example. So let's say example, you have kept the values to be 1 plus Rg by R shunt to be 1000. So what is the meaning of this? So your galvanometer, which is there, let's say this thing has 0 milliampere, 1 milliampere. Remember, it measures always in milliamperes or microamperes. So it actually measures Ig. So now what I'm suggesting, erase all these numbers and multiply each number with 1000, because capital I is nothing but Ig plus 1 plus Rg. So this number becomes 0 ampere, this becomes 1 ampere, this becomes 2 ampere, this becomes 3 ampere. So whenever the current in the galvanometer is 2 milliampere, the capital I is 2 ampere, isn't it? So even though the galvanometer is measuring Ig, but it is showing you capital I. Is that making sense how we manipulated this? This is all because I is 1000 times Ig. For example, let's say if it is not 1000, but it is 500 Ig, then what will be the values? This will be half ampere. This will be 1 ampere. This will be 1.5 ampere, isn't it? So accordingly, you adjust the values on the, the galvanometer. Is that making sense? So what we did here is your galvanometer is still measuring Ig, but you're making it show bigger values. So what you measure and what you see are two different things. Is that making sense? So in the galvanometer, when Ig is 2 milliamperes, right? Capital I is 2 amperes. So the needle or the galvanometer measures 2 milliamperes. But since you have manipulated the whole numbers on the top, you're getting to see capital I. Is this making sense, everyone? So the idea is pretty straightforward. The formula, there's nothing there. It is a simple formula. But what we did was this. End of the day, the only one who always moves is IG. There is nothing called an ammeter as such. Ammeter is nothing but a galvanometer inside, which has a resistance. It is measuring IG, but it is showing you something else. Is this making sense, everyone? You can just put on this formula. More than the formula, right? Really understand how we have derived it and what is the working behind it. All clear with the working? Next thing, there are certain precautions you have to take while making this. The shunt resistance must be small. Like I said, if you understand the topics are very simple. This is more of a theory today. The first thing, when you make the shunt resistance very small, you get a big range. So range increases. You can measure bigger currents. Why? What is the formula? The capital I, that is the thing which you want to measure, is 1 plus Rg by R shunt. If you make the shunt resistance small, you get a bigger range. Second, if R shunt is small, then maximum current will flow through the small resistor. That means your Ig becomes small, and which is good. I don't want large Ig. Remember, if the Ig value becomes more, the galvanometer will burn. If you keep two resistors in parallel, maximum current will flow through the smaller resistor. So you have protected the galvanometer. This is Ig. We take this is I. This is Rg and this is R shunt. Then we get Ig is nothing but I into R shunt by Rg. It is in that ratio, isn't it? So smaller the R shunt, smaller the Ig, and the better for me. The device is safe. Third, the error decreases. Now, no matter how good an ammeter you make, you will always have some resistance. So technically, let's say if you want to measure the current, you have a battery V and a resistance R. So theoretically, we know the current I should be V by R. But when you go and put an ammeter, the very act of measuring the current messes up the current. If you go and put an ammeter, now the current gets messed up. I dash is V by R plus RA. Because you wanted to measure it, you have introduced a resistance, and that itself actually changes the actual value. And we know the resistance of this ammeter is nothing but 1 by R shunt plus Rg. So if you make the shunt resistance very small, then Ra also becomes very small, so error decreases. These are the kind of questions you'll get in more than one choice measure statements. There, these are the three advantages you get when you keep the R shunt very small. Clear with this? You get maximum range, you get protection because the current becomes small, and the error also decreases. Any doubts on this? Clear, na? Devansh, Ahana? Vihan? Clear? Next thing, voltmeter. So you want to measure voltage. And again, remember the story, the only one you have is galvanometer. There is no other device that we have. So it measures voltage. And is constructed by keeping a large resistance in series. Voltmeter must be placed in parallel so that if they're in parallel, you get the same voltage. So whichever device ka potential difference you want, you have to keep it in parallel. And an ideal voltmeter has infinite resistance. Did we write this? Yeah, ideal ammeter has zero resistance. So how do you construct this? You take the galvanometer and you keep a large resistance, I'll call it RL, in series. So capital I is flowing here, and this is the resistance you want to find. So you want to find the voltage across RL. So this whole package here, this red box, is your voltmeter. This current will be IG. This is straightforward actually. The voltage across capital R is nothing but voltage across RG plus RL, isn't it? Because they're in parallel. The voltage across R is nothing but IG into RG plus RL. There. This is your formula. And this is your multiplying factor, RG plus RL. Same story. What we did in ammeter, we are going to do the same thing again here. So, example, if we take RG plus RL as 10,000, then your ammeter becomes like this. 0 milliamperes, 1 milliampere, 2 milliampere. So this actually measures IG, but now you have manipulated this device to show voltage. This becomes 0 volt, 10 volt, 20 volt. Are you getting this? So every time the voltage is 10 volt, the IG will be 1 milliampere. So the needle will point towards 1 milliampere, but you have erased 1 milliampere and you wrote 10 volt there. Is this making sense? So a voltmeter, right? Galvanometer measures IG, but it shows voltage. Is this making sense? So end of the day, it is always the galvanometer who does everything. You are just manipulating that number there. Is that clear, everyone? That's your second formula there. You can just note it down. Then here also we have to take care of the precautions. RL should be large. One, same thing, range increases. You actually have the same advantages because we use IG into RL plus RG. Second, if you keep a large distance in parallel, current decreases, so IG decreases. Third, error decreases. So whenever you take a galvanometer, you should make sure that RL is large. Clear with this? All clear with this? That's it. So in terms of theory, that is a theory for ammeter and voltmeter. Let's see a few questions on this. That is the best way to do this because as such, there is nothing there in the questions there. Let's see a few questions. Let's start off with something easy. Get them. They're easy. I'll give you a minute. Full scale meaning maximum current. You got an answer? You can type in the chat box to the co-host. Again, remember, just because you use the word ammeter and voltmeter doesn't mean you have to use the formulas. You can, it is simple series parallel V is equal to IR standard stuff. Get them both. You got a minute. Seriously, first one, what happened? Yeah, first was easy, right? Look at that thing. Current is same. So I by 2 into 20 must be equal to I by 2 into RG. The RG is 20 ohms. They're in parallel. They have same current. The resistance must be same. That's it. What is the B part? Is that making sense? Both of them are in parallel. They have same current, so the resistance is same. That's it. Just don't see the word galvanometer and get scared like, oh, I have to use something. There's nothing there. Right, Aditya. Right, Vignachit. How to do the B part? Yeah, most of you got it. See the first thing. A galvanometer resistance 20 ohms and full scale, then zero point 0.2 volts is there. So he's saying Ig is voltage. When you apply 0.2 volts across the 20 ohms resistance, you get a full scale deflection. So this is 0.2 by 20. So 0.01 ampere. You're getting it? So the first statement indirectly gave you Ig ka value. And then you're done. So capital I is equal to Ig plus 1 plus Rg by R shunt. That's it. You know everything. So you want to measure 10 amperes. That's your capital I. Ig is 0.011 1 plus Rg is your 20 and R shunt you have to find. I think this thing comes out to around 20 by 999. You can approximate it to 0.02 ohms. B answer. Got this? So the thing is you need to find Ig from the first data point and then just use your regular formula. All clear with this? Clear, na? Ahna? Arush, Adi, Saish. Let's see a few more. That's it. In this thing, right? Main thing, if you do some 7, 8 problems, you get the hang of it. It is pretty easy. Let's try this. So we have a milliammeter of range 10 milliampere. Resistance is 9 ohms, but there are 3 terminals. Get this, you got a minute. What is the catch here? Now see, if you blindly remember the formula without understanding, you will be trapped. Tell me one thing. If you connect the battery between A and B, right, this 0.1 will become the shunt resistance. And if you ask this resistance, what is RG, what will it say? It will think this 9 and 0.9 are part of one system, isn't it? You're getting it. So depending on which two terminals you connect, for example, see, if you connect the terminals between B and C, 0.9 will be the shunt resistance and 9.1 will be RG. Are you getting it? So if you keep some resistance in series to the galvanometer, that resistance also becomes a part of RG. If you just go back to the derivation, you'll realize that. Look at in this derivation, if you had kept something in series here, R dash, then this guy will be IG into RG plus R dash, isn't it? So the shunt resistance doesn't care that RG is, RG is actually a combination of all the resistances series to the galvanometer. So when you connect between A and B, this will be your shunt resistance. So R shunt will be 0.1 ohm. And here, the shunt resistance will think 9 plus 0.9 is RG. That's 9.9 ohms. You're done. So IG is 10 milliampere. You want capital I. Put it in the formula. Sure, everyone? This thing comes out to be how much? 1 ampere. Is their logic making sense? So don't blindly remember RG is 9 ohms. The shunt resistance doesn't know who is 9. It will think 9 and this 0.9 together are part of the same system. So it will take 9 plus 0.9. Is that clear, everyone? Can tell me if I connect between A and C, what is RG and what is R shunt? If I connect between A and C, what is RG and R shunt? R shunt will be 1, RG will be 9. Making sense? So depending on which terminals you connect, you can get different ammeters in this case. Going ahead, Arnav, Pushkal, play with us. Next thing. Let's get these two. Least count. This has done and comes in instruments. This is the smallest measurement you can make. Or the length of the division. So this voltmeter can measure anything in the terms of 0.1, matlab 1, 1.1, 1.2, 1.3. Get them both. You got 2 minutes. Right, Puruja. Right, Ishana. Right, Pushkal. Right, Vignachit. Near Aditya, that is wrong. Niharika, right. Right, Vivan. Yeah. Yeah, I think D is done. Get the E1 now. So what to D? A galvanometer has a coil of resistance 90 ohms. So this is RG. Full scale deflection 10 milliampere. This is IEG. 910 ohms is connected in series with a galvanometer to make resistor voltmeter. This is R large. So yeah, so V is equal to IG into RG plus RL. So IG is 0.01, RG is 90 plus 910. This is 10 volt. You have 10 volts and each division measures 0.1. So just divide them. So number of divisions will be 10 volt by 0.1, which is 100. What about E? Let's see. Now look at this thing. In the circuit shown, the resistance of the voltmeter is 10,000 ohms. That of ammeter is 20 ohms. The ammeter reading 0.1 ampere. So this current is 0.1 ampere. This thing is measuring 12 volt. That means voltage across the resistance plus voltage across the ammeter is 12 volt because they're in parallel. This is nothing but 0.1 into R. This is 0.1 into 20 is equal to 12. And then you get R is equal to 100. Easy. These are easy, mains and CET level questions. Like technically, they really can't ask too much on this until unless you combine this with something else, instruments and stuff. But yeah, we should know these basics. Clear with us? That's the reason I'm keeping all of them in one question only. Yeah, but you need to do practice. Without practice, still you will do mistakes there. This G is a good question. You can put a star for this. Now in G, I'll change the question here. Listen once. For these four devices that you have, we have two ammeters and two voltmeters. The question is this: arrange them in the ascending or descending order of resistance, meaning the largest resistance to the least resistance. That would be a really good question. So we have four devices: 10 ampere, 10 ammeter, 10 ampere ammeter, 5 ampere ammeter, 5 volt voltmeter, 10 volt voltmeter. These four devices, arrange them in the descending order of resistance. There, get them both. Yeah, F is easy. Get the G. So what is Ohm's law? V is equal to IR. So you need to find the voltage and the current. Voltmeter must be in parallel. Ammeter must be in series. Easy. Get me the answer for G. arrange them in the descending order of resistance. The biggest one to the smallest one. Get that, I'll give you a minute. Now, before jumping into more technicalities, just ask yourself this question. If it is a fight between ammeter and voltmeter, who will have more resistance? Between an ammeter and a voltmeter, who should have more resistance? Look at this thing. For an ammeter, the resistance must be small. For an voltmeter, resistance must be large because it is in series. So if it is a comparison between voltmeter and ammeter, voltmeter is the largest. Fair enough? Now the question comes, between the two voltmeters, how do you compare? And that's what we wrote actually, one of the things. Yeah, Puroj, I think you got an answer. Oh, yeah, most of you got it. See. So for an voltmeter, RL must be large so that you get more range. So that means between two voltmeters, whoever has more range has more resistance, isn't it? Similarly, for ammeters, the one with a more range will have less resistance because R shunt must be small for more range. For voltmeters, larger the range, larger the resistance. So between two ammeters, the one with the more range must have smaller shunt resistance, so smaller resistance. That is how you compare. So voltmeters are the biggest and D has a more range, so D is greater than B. Between the two ammeters, 10 has a more range, so that should be the smallest, so DBCA. Sure with that? So the largest range voltmeter will be the biggest and the largest range ammeter will be the smallest. Clear enough, Vignajit? Clear with this? That's a good theoretical one. Clear with that, Arush, Adi, Ahna? Clear? Ishana, Pratik? Next thing.
Sir, could you explain the ammeter part of the previous question again?
So tell me one thing, for an ammeter to get more range, should you put small shunt resistance or big shunt resistance?
Smaller shunt resistance.
So smaller the shunt resistance, more the range.
Huh.
So between 10 ammeter, 10 ampere ka ammeter and 5 ampere ka ammeter, the bigger the range should be smaller the resistance.
Yes, sir. Yes.
Make sense?
Yes, sir.
Let's get these two. H is easy. This I, let me change the question a bit. There. I made two circuits. Get them both. Yeah, H is easy. H is something which I just explained. Pratik, clear so far? Yeah. Vivan, Abhinav, clear so far? Great. Yeah, first is easy. Ammeter should have small resistance, voltmeter should have large resistance. What about the ith question? Two for these to find R. Remember, these are non-ideal. What is the catch here? In the circuit shown, the reading of the ammeter and voltmeter are 4 and 20. Look at the problem here. This guy is showing 4 ampere, great. So there will be some current in the voltmeter because it is non-ideal. So this current will be 4 minus I. So when you write V is equal to IR, understand the meaning of that. V is the voltage across the resistance and R is the current in the resistor. So this will be 20 and the current will be 4 minus I. This will be greater than 5 ohms. Is that making sense? Because the voltmeter is in parallel, it is measuring the exact voltage, but the ammeter is actually showing the current in voltmeter plus the resistor. 4 ampere is not the current in the resistor. That's a current in both the resistor and voltmeter together. That means in the resistor, the current is actually less than 4. Therefore, the resistance is greater than 5. Is that making sense? Similarly, if this is 4 ampere, the current is right, but the voltmeter is measuring volt VA plus VR. So R will be 20 minus VA by 4. This is less than 5. So this comes a problem now. You want to measure current, I'll use ammeter. If you want to measure voltage, I'll use voltmeter. But if you want to measure resistance, this is a bad idea. If I use ammeter and voltmeter, in real life, they're always non-ideal. You're always going to get an error. So we need to find something better to find resistance rather than an ammeter and a voltmeter. That comes our next device, Metabridge. So if you want to measure resistance, using ammeter or voltmeter is generally not recommended because either way you'll get an error. Is this clear, everyone? H and I? Then the next thing is a Metabridge. So Metabridge is used to measure resistances. Again, the concept is simple, but there are some pretty good theoretical points on this. So a Metabridge is used to measure unknown resistance. Using the principle of Wheatstone bridge. So we have some steel frames like this. The equipment kind of looks like this. So these are steel frames. We have a wire here. So we have an unknown resistance here, Rx. And we have a known resistance, R. So you want to find Rx. Battery is connected here. We call it a meter bridge because generally use 1 meter, but yeah, you can take any length. This is a wire with uniform resistance R0 and length L. And we have a galvanometer. So this arrow pointy thing, right? We call it, it's a jockey. So jockey, right, is that pointy thing which can move on the wire. So what is the whole story? So what we do, we keep on moving this jockey here until the current in the galvanometer becomes 0. So that is how we do the experiment. You take this jockey, you keep moving it from one place to another place. Till Ig becomes 0. So when this happens, right, they use the word bridge is balanced. So be careful. Sometimes they'll say like this, the bridge is balanced. So it is understood the galvanometer mein current has become 0. Now, if you see the whole concept, it is done actually. So this part is one resistance. This part is one resistance. Rx is one resistance. R is one resistance. If the current in the central resistor is 0, isn't this a Wheatstone bridge? So then I can simply use the ratio and finish it off. Now the advantage of this thing is what? A galvanometer is non-ideal, isn't it? It has some resistance, but the current is 0. So it doesn't matter. You're getting it? Even though the galvanometer is non-ideal, which has some internal resistance, since the current is 0, it won't create any voltage. So it's fine. There's no problem with that. Is the setup clear, everyone? Any doubts with the working? Clear with this? So I'll just draw a simplified circuit. This is Rx, this is R, this is X, this is L minus X. This is a Wheatstone bridge. Then we can simply use Rx by, that will be resistance per unit length R0 by L into X. R by resistance per unit length R0 by L into L minus X. You end up with Rx is equal to R into X by L minus X. There. If I just know the lengths, I can find the unknown resistance. And if you see a few things here, the balancing length doesn't depend on the cross section of the area of cross section. You take a thin wire or a thick wire, it doesn't matter. Since it is a ratio, it gets cancelled off. So balancing length is independent of area of cross section. Yeah, just make sure the wire is uniform though. So there was a question like that. The radius of the potentiometer wire or the balancing wire has doubled. Then what will happen to the balancing length? Nothing. Second thing, what happens if you increase the length of the wire? Instead of using length L, what if you use 10L? If length of the wire is increased, you actually increase the accuracy. We get more precision. That is, we get more decimals. For example, see, let's say if I use a 100-volt battery for a 1 meter wire, how will the numbers be? For every 1 centimeter, I'll use 0, 1, 2, 3, so on till 100. That means here all the values will be like 1 volt, 2 volt, and 3 volt. But same thing, if I use 100 volt for 10 meters wire, then your voltage car readings will be basically the least count decreases 0, 0 0.1, 0 0.2, 0 0.3, and so on. So here the least count is 0.1. You get more precision. Here least count is 1 volt. So if you use a longer wire, you can get more precision. Is that making sense, everyone? हाँ, मतलब ये difference था. For 1 meter, let's say you got a length of 40 centimeter and 60 centimeter. If you use 10 meters, you'll get 4 meters and 6 meters. The ratio won't change, but the value becomes more precise. Clear? Precautions. Now, when you're using meter bridge, there are a few precautions you have to take care. So as such, meter bridge ka concept is easy, but these are the kind of questions you will get in theoretical parts. First thing is end correction. It has its own errors. The thing is, when you're tying that wire, you actually use some part of the wire to tie it or connect it. Since some length of the wire is used for connecting, that actually creates an error. We have to include that also. So they will give like this. They will say in a meter bridge, the balancing length is 40 centimeters, and the left end correction is 2 centimeters, and the right end correction is 1 centimeter. They'll use words like this. The terminology is important. And you're seeing a lot of new terminologies today. Jockey, shunt resistance, end corrections. So we'll keep hearing these words. Bridge is balanced. So this end may, right? This wire is connected here. This wire is connected here. So they will say right end correction is 2 centimeters. Left end correction is 1 centimeter. So this wire is actually not 100, but 103. That's it. So the same story. So when you balance, this is what you write. Rx by total resistance by total length. This will be X plus 1. This will be L minus X plus 2. Solve and you'll get X answer. Clear with that? So you just have to include that additional wires there. Second thing, the jockey must not be dragged on the wire. This is fine. This is not a big deal, but because if you start dragging this, there is a chance the wire will become non-uniform due to wear and tear. You should always lift the jockey and put it at different places. So lift it at 50, put it at 51. Lift it, put it at 52. Lift it, put it at 53. That's how you don't drag it on the wire. Third one is the most important one. There is a question like this. In a meter bridge, while balancing, in which part of the wire should the bridge be balanced? The first 1/3, middle 1/3, or the third 1/3? Meaning, if there's a 100 centimeters of wire, in which segment? 0 to 33, 33 to 67, 67 to 100. In which part should the bridge be balanced? Now, technically, when you look at the formula, right, it really doesn't make a difference. Like it feels like X could be anything, but this is related to errors. So something like this happens. So I'll give you the answer first. The bridge must be balanced in the middle 1/3. We'll see why. I don't remember where I saw this. Bits or means or CET, I guess somewhere. This is a good one. They can actually ask, and even at advanced, they can give some numbers and play with this. So let's say we have an unknown resistance here, Rx, R. Let this be X and let this be L minus X. End of the day, this X and L minus X are actually measurements. So Rx will be R into X by L minus X. Put log on both sides and differentiate errors. So we have delta Rx by Rx will be delta X by X plus delta L minus X by L minus X. Errors are always additive. This turns out to be delta X by X plus delta X by L minus X. Now look at the problem here. If you balance the wire pretty close to zero, let's say 1 centimeter, 2 centimeter, then X becomes very small. Then this error becomes high. If you balance it pretty close to 100, 97, 98, then L minus X becomes very small. This will become pretty high. You're getting the problem? You get it close to zero or you're getting close to the other end, the ends will always create huge errors. Because see, the final answer when you report, right, you'll report Rx plus or minus delta Rx, na? So the delta Rx error goes off. So that is the issue there. So if X or L minus X is small, the error becomes large. So if you want the least error, you should balance exactly at the midpoint. That is another question. At which point on the meta bridge the error is minimum? You can do maximum minimum for that function, you will get when L minus X is equal to X. That is a midpoint, the error is minimum. This will be more than one Chwarsky statement, one of the statements. But it is not feasible every time to get exactly at the midpoint. So we say like middle 1/3 is okay. So middle 1/3 will have less error. But the closer you're getting to the midpoint, the less error you get. Clear with this? Yeah, that is the whole theory about meta bridge. Is this clear, everyone? Take a small break, come back by 9:40. Take a 5-minute break. Any doubts so far? Okay, come back in 5 minutes. Let's start off. So on this thing, there's really not much, but let's see a question. Let's say we have 2 ohms, we have 4 ohms. So let's say this potentiometer wire, right? Instead of putting a uniform wire, you messed it up. You kept R is equal to R naught into 1 plus X by L. So we got a wire which is non-uniform resistance, which is changing with X coordinate. R naught is resistance per unit length. And let this distance be X. Find X if the bridge is balanced. Meaning when Ig is 0. Let's get this. Remember, you can't use this formula anymore, but the concept is still same. If the bridge is balanced, it forms a Weierstrass bridge. So in these things, right, the main thing, like, never mug up the formulas. Always understand how it is working, because if something changes, you should know where to do the adjustment. You got an answer, you can type here in the chat box. So let this be R1, let this be R2. So what is the concept? It still forms a Weierstrass bridge. So 2 by R1 is 4 by R2. So R1 by R2 is equal to half. Root 2 minus 1. Okay, let's see. Now what is R1? Integration, everyone. Variable resistance. So it is R naught into 1 minus X, 1 plus X by L into dx. Isn't it? But R1 is what? From 0 to X. What is R2? R2 is also same, 1 plus x by L into dx. The limits will change. So R2 is a resistance from x to L. So limits will go from x to L. Getting the difference? What will change is the limits. So R0 into 1 plus x by L into dx will give a small resistance, and all are in series. So you can just integrate them. So this ratio will be half. R0 will cancel. When you integrate this, you'll end up with x plus x square by 12 by, this limits will go from 0 to x. X square plus x by 12 limits will go from x to L is equal to half. Cross multiply. That would be 2x plus x square by L. This would be L plus L square by 12 minus x plus x square by 12. Shifted to this side, you get a quadratic. 3x square by 12 plus 3x minus 3L by 2 is equal to 0. 3 goes off. This will be 12x minus L square is 0. Minus 2L plus or minus B square. 4L square plus 4L square by 2. How much is this? Root 2 minus 1L. Clear? There. So the idea is still the same. That ratio will still be equal to 2:4. You just have to integrate for the resistances. You just can't. The limits will change. 0 to x and x to L. Clear with this? Yeah, so generally MetaBridge may either they can ask the precautions or they can do something of this sort. They can mess up the, instead of a non-uniform wire, they'll give you something non-uniform. Yeah. That's about the MetaBridge. Now, part of the MetaBridge, we also have something called a post office box, but I think that we will see in the end. It is just a small theory there. But there is one more important thing, a potentiometer. Now, potentiometer, technically, they removed it from the portion last year in mains and advance, but they asked in mains. It is still there in bits. And I don't trust them, so they'll do something next year also. And anyway, it is not a difficult thing. They can always ask this as a paragraph and ask. So we will still do potentiometer. It's quite an important thing. So let's do potentiometer, and then we'll come back to the post office box. So listen carefully. It's again not a tough thing, but quite an important thing. So potentiometer, now see, you want to measure current, we have ammeter. You want to measure voltage, we have voltmeter. You want to measure resistance, we have MetaBridge. What if you want to measure EMF of a battery? If I give you a battery and ask you what is the EMF and what is the internal resistance, we need something. So we use a potentiometer. So it is used to measure the unknown EMF and internal resistance of a battery. So the first thing in a potentiometer, right, the circuit. If you know how the circuit looks, it becomes quite easy to solve the problems. So circuit has two parts. This is E prime. This is R prime. So this is the primary circuit. So this is your standard circuit, which you should know. This wire resistance is R0 and the length is L. This is your potentiometer wire. This is your EX, the unknown resistance. This is your RX. This is your galvanometer. This is some R known. This is your switch. The moment someone says potentiometer, you should know the circuit. So R0 is the resistance and L is the length. So if you look at this, I know everything except EX and RX. EX and RX are unknown. Everything else is known. So the first thing in potentiometer, you should know the circuit. Second thing, there's only one concept here. If you know that one concept, potentiometer is done actually. Let's see what is that. First thing, let's find the unknown EMF. So to find EX, keep the switch open. Open the switch and balance the bridge. What do you mean by balance the bridge? Current in the galvanometer is 0. So this switch is open, so that bottom resistance is useless. This is E prime, this is R prime. The current in the galvanometer is 0. Now listen to this thing. If the current in the galvanometer is 0, the current in this branch is also 0. Do you agree? Because see, where will this current come from? If this current comes here, it can't go this way. It can't go this way because IG is 0. Then this current has to be 0 in this branch. Everyone agrees? That means whatever current that flows from the primary battery will keep flowing only in the upper circuit. Is that understood? There will be no current in the EX. Then if you look at this point here, this is A. Let this point be C. This point is A dash and let this point be C dash. So capital I is nothing but E prime plus R prime plus R naught. And can I make this statement? The voltage across AC must be equal to voltage across A dash, C dash. Do you agree with this statement? Look at this thing, Y. Point A and A dash are connected by a wire, so they both are equal. Point C and point C dash are connected with the galvanometer, but current is 0. If current is 0, that means there is no potential difference. Therefore, C and C dash also must be same. That's it. If you understood this one thing, I think potentiometer you can handle it. A and A dash are same. C and C dash are same since IG is 0. Therefore, voltage across AC is equal to voltage across A dash, C dash. What is voltage across AC? Current into resistance across AC. What is this? EX minus I into RG. But this term is 0 since I is 0. Capital I is nothing but EP by R prime plus R naught. RAC is nothing but resistance per unit length into X is equal to EX. I know everything here. EP R naught by RP plus R naught into L into X. EX is proportional to X there. I don't want you to remember the formula, but I want you to understand this part. If you know your circuit and if you know this point, potentiometer can handle everything. Is this making sense? And we can clearly see here the voltage, whatever EMF that you get, that will be proportional to the balancing length. So when you're in a lab, right, we actually don't use this one. We use a version of this. Let me show you that also. That was asked as a PYQ once. But first have a look at this. Ask me if you're confused anywhere. since there's no current in EX ka battery, whatever current flows will keep flowing only in the upper circuit. Any doubts on this pitch? Pushkal, Ansh, Arnav, Saish, Adi. Clear? Got this? So how do we actually use this? Now, when you're in a lab, right, we are really not interested in calculating EP, RP, R naught. Who will calculate all these values? So what people do, we actually use two cells. We use two cells, E1 and E2. Let's say EMF is the unknown one. This is what you want to find. And take one more cell whose EMF you already know. Then what you do, repeat the experiment, keeping them in same polarity and reverse polarity. Let me show you how will the picture look like. Let the balancing lengths be L1 and L2. This was a question in the exam. When they're kept in the same polarity, the balancing length was L1. When they're in the opposite polarity, balancing length was L2. Find E1. So this is how the thing looks like. So you keep both the batteries in the same polarity. So E prime Rx, so this is how you keep it plus, minus, plus, minus. This is E1, this is E2. This is plus, minus, minus, plus. So both are opposite, so the EMF will actually subtract. Let this length be L1. Let this length be L2. So from here we get E1 plus E2 is proportional to L1. E1 minus E2 is proportional to L2. They have the same proportionality constant, just divide them. So E1 plus E2 by E1 minus E2 is L1 by L2. You can solve this, you'll get E1 ka value. The advantage of this method, I don't care about the EMF of the primary battery. I don't care about RP. I don't care about R naught. I need not know anything. Is this making sense? All I need is one known battery and I need to know the balancing length and I'm done. So this was a question actually in the mains also. There are two cells of EMF E1 and the second is some 10 volt. When they're kept in the same polarity, the balancing length was 60 centimeters. When they're in opposite polarity balancing length was 20 centimeters. Find E1. That was a question directly. Those who understood, they could have solved it, or else you literally have to do the whole thing. But is this clear, everyone? This is how you can find EMF of an unknown battery. This comes because E is proportional to X. And we got that because VAC is equal to VA dash C dash. If you ask me, this is the primary one. As long as you understand this part, you can handle some varieties. We'll see. Clear with this? Any doubts on this page? Going ahead. Next thing, to find the internal resistance. So we got EX, we want to find RX now. Now what you do, close the switch. and balance the bridge. Again, you have to draw the circuit. This is how the circuit looks like. This is R. This is EX, which we have actually found out. This is RX. This is EP. This is RP. This is R0. This is length L. This is X. Fine. Now see what happens. Since the bridge is balanced, the current in the galvanometer is 0. If this current is 0, this current is also 0. That means whatever current flows in the primary circuit will remain in the primary circuit. Similarly, whatever current flows in the secondary circuit will remain in the secondary circuit. Both the circuits will behave independent of each other. That point is clear. Once you got that, the story is still the same. This point is A and this point is A dash. Both are equal. This point is C and this point is C dash. Both are equal because Ig is 0. So I is nothing but E primary by R prime plus R naught. Small I is nothing but Ex by Rx plus R known. If this point is A dash, this point is also A dash, and this point is also C dash. You're done. The voltage across AC must be equal to voltage across A dash, C dash. So this will be I into resistance across AC. This is small I into resistance across the known resistance. This EMF and this potential difference are same, isn't it? The battery EX, RX, and RK are in parallel. What is this thing? EP, RP plus R naught. This will be R naught by length into X. This is EX by Rx plus RK into RK. There, I know everything here except Rx. Solve this, you'll get an answer. Again, like I'm saying, I don't want you to remember all this result. I just want you to remember this concept. Understand how the circuit looks and understand that AC is equal to A dash C dash. If you know these two, you can solve it. Have a look at this. Sure, everyone. Let's see one question. There's still more theory, but I think we'll do one question that you should get a hang of it. But any doubts on this, what we did? I hope everyone is convinced with this part, right? AC is equal to A dash A dash. Let's do one question. There, I think if you got this, this will cover the whole thing. Let's get this. One thing, in case you don't know, what is a rheostat? A rheostat is a variable resistance. You can change the resistance from 0 to 10 in this case. So rheostat is a device where you can adjust the resistance. Let's get this. I'll give you 2 minutes and 2 minutes for each part. That's what I'm saying. Potentiometer, even though they removed it, it is really not something out of the boundary. All they need to do is just give a circuit and say, this is potentiometer, and you're done. Then they'll start asking whatever they want. Let's get this. Always draw a circuit. Always redraw a circuit helps. 6. Let's see the first one. Let's draw the circuit again. You're keeping initially at minimum resistance. So the switch is open. So I'll just not draw that. So this is 10 volt. This is 1 ohm. This is 9 ohm. This is 12 meters. This is 4.5 volt. This is small r. Since the bridge is balanced, this current is 0. This current is also 0. Whatever current flows here will flow only in the primary circuit. I is given by 10 by 1 plus 9. That's 1 ampere. Let's call this point A and this point P. Then this is also A dash and this is also P dash. So voltage across AP must be equal to voltage across A dash, P dash. So this is current I into resistance of AP. This is 4.5 minus IR. I is 0. This is 1 and this is 9 by 12 into AP is equal to 4.5. AP is equal to 6 meters. Easy. That's it. There is nothing new that you're doing. Just draw the circuit and you say always AP is equal to A dash, P dash, and you're done. That is the whole theory of potentiometer. Now can you do the second part? Right, Puroj, you got the second part. Try others. I'll give another 1.5 minutes for the second part. Now this time the rheostat is maximum and the switch is closed. Redraw the circuit again. And he's saying it is getting balanced at 8 meters. Then find the internal resistance. This problem is literally whatever I taught you. Switch open, switch closed, EX, RX, everything. Get it? You got. Vignachit. Right, Niharika. Yeah, we already have 3 answers. Try others. I'll give you a minute more. Yeah, right, Ishana. Let's draw the circuit. This is 10 volt. This is 1 ohm. This is 10 ohm. Rheostat is maximum. 9 ohm. This is 12 meters. This is 4.1 and this is 2 ohms. The bridge is balanced, so current in the galvanometer is 0. This current is also 0. Whatever flows here stays on the top. I is equal to half ampere. Whatever current flows here will stay at the bottom. Both the circuits are independent of each other. So small I is 4.5 by R plus 2. If this is A dash, and this is also A dash, all are equal actually. If this is P, then this is P dash and this is P dash. Voltage across AP must be equal to voltage across A dash, P dash. This is nothing but I into resistance of AP, and I think they gave you AP is 8 meters. This is small I into 2. This is half, and this is 9 by 12 into 8. Small I is 4.5 by r plus 2 into 2. 2 za 4 za, we will get r plus 2 is equal to 3. Make sense? All got this. There's nothing there. Just get the circuits V is equal to IR and solve. We are just doing that only. Any doubts on this thing? Let's see one more, and then we will do a bit of theory also. Let's get the same question. I think if you got this, you understood. Let's get this. Switch S2 is open. It shows no deflection for L by 2. When switch S2 is closed, the galvanometer shows no deflection. So this is the primary circuit. The upper one is a secondary circuit now. Primary and secondary, they just kept up and down. Get this. So here they're asking the primary battery ka voltage and internal resistance of the 6 volt. Just have to draw the circuit. So when the switch is open, so current is 0. This current is 0. So whatever flows here will flow here only. And this resistance B, R naught, and length is L. So I is nothing but E by R naught. If you take this point as A and this point as B, this is A dash and this is B dash. Voltage across AB is equal to voltage across A dash, B dash. This is nothing but E by R naught into R naught by 2 because it is half of the length. And this is 6. So you can actually directly see and guess it, isn't it? Proportional to length, they'll half the length, double the voltage, done. But okay, I'm just showing you. Then read out the circuit again. Yeah, most of you did get the answers. Yeah. Now you're saying this is 5L by 12. Same story. This current will remain same. This is 12 volt. This is 10 ohm. So this current will be independent of this. So I will be 6 by R plus 10. Capital I. You don't need to do this, but okay. 12 by R naught into L. Just name the points again here. A, this is A dash, this is B dash, and this is B. VAB is equal to VA dash B dash. This is 6 by R plus 10 into 10. There you got everything here. And you get 2 ohms. B answer. Check. Clear with this? This is also A dash, this is also B dash. So find the voltage across this thing. That should be the voltage across this thing. Clear with this? There's nothing new I'm doing. I'm just repeating the same thing if you see. Any doubts on this? All clear with the potentiometer thing? No. Let's get back to this, a little bit of a theory. So if you see this, when the switch was open, the internal EMF EMF became equal to L1, the balancing length. When switch is closed, the balancing length became I into R known proportional to L2. And we know I known is nothing but, or let me write like this, EX minus I into RX proportional to L2. I is nothing but EX by RX plus RK. So if you divide them, this is another way of asking the question. This is L1 by L2. If you substitute this value there, EX actually cancels out. EX goes off, and this turns out to be Rx plus RK by RK is L1 by L2. So we get Rx by RK is equal to L1 by L2 minus 1. There. This is the relation between the balancing lengths and the known resistance. So if someone gives you the balancing length and they give the known resistance, you can figure out Rx without that Ex and all that stuff. Is this making sense, everyone? So this is another way of asking. When the switch was open, balancing length was 60 centimeters. When the switch was closed, the balancing length is 40 centimeters. And the known resistance is 2 ohms. Find the unknown resistance. Now, instead of drawing the whole circuit again, trying to figure it out, yeah, the same thing. You're just manipulating the equations. Clear with this? I hope the calculations are right. Looks right. Any doubts on this? There, I did nothing here. I just took up this formulas and I just did the same thing. Now in potentiometer, there are a few precautions you have to take. The precautions are more important. So listen to this carefully. First one, you should make sure the E primary is greater than E unknown. What happens if you don't do this? Let's see with an example. I'll not take any internal resistance. Let's say you have taken a battery which is 20 volt and let's say you're trying to balance 30 volt. For simplicity, I'll assume this is 0. Then this will be 20. This is also 0. This is also 20. Meaning, how will the numbers be? The numbers will be like 15, 10, 5, 0, something of that sort, isn't it? Now, this point is also 20. Can you tell me what will be the potential of this point here, the green one? Minus 10, isn't it? If the battery ka potential is 30 and the positive terminal is 20, then the negative terminal will be minus 10. But can you find minus 10 somewhere on the bridge? You cannot find. That means Ig will never be 0, means bridge will never be balanced. So you can't use any of the formulas we are using. So we can't find minus 10 volts on the bridge. This is what happens if your unknown EMF is greater than the primary battery. Ig will never be equal to 0. Bridge is unbalanced. Clear with that? So that's your first precaution. Make sure your primary battery always has more EMF than the second one. Second thing, the batteries must be in the same polarity. EP and EX. Must be in same polarity. What do you mean with that? Let's take an example again. Look at this. Here, this is plus, minus, this is plus, minus. So that's the same polarity. Plus, minus, this is minus and plus. Let's say this is 20 volt and this is 10 volt. There, I took care of the precaution one. The primary battery is greater than the secondary one. If I take this as 0 potential, this is 20 potential, this is 20, this is 0. Again, same story. This is 15, this is 10, this is 5. If this is 20, what will be the potential of this terminal now? Plus 30, isn't it? If you give the battery in reverse potential, the potential adds up. Even though you are smaller than the EMF, you are going to get more. Again, same story. Bridge will never be balanced. You won't find plus 30 anywhere on the bridge. That is the second precaution you have to be careful. If the batteries are in reverse terminals, you can never find a balancing point. If Ig is not 0, then you can't solve. That means the currents will actually start flowing into the circuit. So is this clear, everyone? The third precaution is the most important one. the R naught, which is the resistance of the potentiometer wire, must be much, much greater than R primary. Again, let's see with an example. There, I kept them in the same polarity. Let's say this is 100 volt. This is 50 volt. There, E primary is greater than EX, satisfied. Same polarity, satisfied. Let's say for convenience, let's say RP is 20 ohms. And let's say your R naught is also 20 ohms. Now what happens is, if you take this point as 0, this point will be 100, this point will be 100, and this point will be 50. So this is the problem there. Since RP and R naught both are equal, each of them will take 50 volts each. The battery will divide the voltage 50-50 across each of them. So if you look at the wire, the bridge here, even though it looks like you're using 100 volt battery, in reality, you're getting only 50 volts ka voltage, isn't it? Is that making sense? Even though you have a 100 volt battery, the bridge can balance only 50 volts. Now look at the potential here. If this is 100, let's take this as 60 volts. This point will be how much? This point will give you plus 40. You can't find 40 on the bridge, isn't it? Making sense what happened? The bridge won't be balanced here. So same story here. So the reason is this. The potential difference will be split between both of them. So potential difference across the wire is 50 volts. So even though we are using 100 volt battery, it behaves like 50 volt battery because of RP. So generally, when you take the values, what we do, we will take something like RP is equal to 1 and R naught is equal to some 200 or something. So this can be neglected. If your internal resistance becomes equal to R naught, we'll have a problem. All clear with this? Any doubts on this? So these are the 3 precautions you have to take. That's about the potentiometer thing. A few more problems are there. We can do that. We'll do them in the next class. So we will do another 2 or 3 problems. I know there are too many things today. Definitely make sure to go through this. Whatever we did today, instruments actually have a pretty high weightage. In this, they can mix up, vernier calipers, screw gauze also, and they can ask stuff. So that we will see later on. When I teach you vernier calipers and screw gauze, I'll show you. There, so we saw ammeter, voltmeter, then we saw meter bridge. There's still one more, post office box. I think that we can do in the next class. Then let's do one problem here. Let's do this. Let's finish off. Last one for the day. This will wrap up. Next class, maybe I'll take another 15-20 minutes. We'll wrap up the chapter. Then we'll start off with ray optics. We will take a small break from electromagnetism, go back to ray optics, and come back. The picture is not clear, but this is positive, this is negative, this is positive, this is negative. Even E2 are in reverse polarity. Let's get this. How do we do this? Anyone remembers? You can replace this whole thing with one battery, isn't it? Last class I taught you. What is the formula? E equivalent E1 R2 minus E2 R1 by R1 plus R2 because they're in reverse polarity. So E1 is how much? 2. R2 is 6. 4 and 2 by E2 plus 6. That is 12 minus 8, 4 by 8. This is half volt. So that whole setup you can replace with an half volt battery. That is the advantage if you know that. Nay, to literally have to take I1, I2 and solve all that stuff. Can be done, but so this is an half volt battery with an internal resistance R. E0 is 12 volt. This is 8 ohms. The resistance per unit length is 4 ohm per meter. Perfect. So this is A, this is B. So VAB is half volt. So I into 4 into X is half. I is nothing but 12 by 8 plus the length of the wire is 4 meters. So 4, that is 16. That is half. X is 1/4 meter or 25 centimeters. Yeah. Got this? Yeah, this is something we did last class only. Combination of batteries. I told you it will come again. Same polarity, reverse polarity. Don't forget this. Saves you time. But in case you don't remember this, then the only option is this. You literally have to solve. Let the current be small I, then you find this current. It's not difficult. You can find the potential difference, then E minus IR1, and then you can do it. Clear with this? There, that's a bit about potentiometer. So next class when we catch up, maybe we'll do another 1 or 2 problems on this. Then I'll teach you the post office box. That is also a small concept. We should wrap up another 20-25 minutes, and then we'll start off with ray optics in the next class. Okay, with that, we'll wrap up for the day. So make sure to go through this. Technically, I think current is almost done. You can start solving if you have not started. Right? Don't take again too much time. Try to wrap up this thing in another 1 week. By next Friday, at least try to finish off current ka whatever solving is there. And do remember there's a test online till Thursday, so make sure to give. So yeah, any doubts, anything you can stay back and ask, also free to leave. I'll see you again on Friday, same time. So take care, stay safe. Any doubts in the class notes, plus you can ask. And then Vihan.